Ever since the brilliant pioneering work by Dr. Alan Handyside in England, as well as work by Jean Lou in Brussels, Belgium, it's been known that you can create a hole in an embryo like you have just seen, and then remove one or even two of the cells after 3 days of development, and that embryo, that is the remaining 7 or 6 or possibly even 5 cells of that embryo, will go on and develop into a normal baby no differently than if no cell had ever been removed. This is because at this early stage, that is 8 cells, each one of those so-called blastomeres, each one of those cells of the day 3 embryo is totipotential. Each one has the same genetic potential to become a baby. Therefore, as you see here in the first of 3 day 3 embryos, if we remove 1 or 2 of those blastomere cells, we can genetically test them for disease processes and determine whether that embryo is going to be a viable, healthy baby before replacing it back into the mother. Now that sounds a little bit easier than it really is in practice, because you'll see that each of these 8 cells is fairly tightly connected to each of the other ones, and it requires extremely gentle, delicate micromanipulation at 400x magnification with these little pipettes that are invisible to the naked eye in order to gently tease one of these cells out of the embryo without damaging either it or any of the other 7 cells. You'll notice that all the motions are extremely delicate and very slow under 400x microscopic magnification. You can see this cell has been beautifully pulled out of the embryo now, intact, so that it can be genetically tested. And the embryo has not suffered any damage in the process. Now we can remove another cell, converting this from a day 3 8-cell embryo into a day 3 6-cell embryo, and this will in no way damage the ability of that embryo to develop into a normal baby. Yet we will have 2 cells that we can genetically analyze so as to determine whether or not this would result in a baby that has a severe and lethal genetic disease. You can see now that the second blastomere is being very, very gently teased out of the zona pellucida, that is the outer shell of this embryo, and we now have successfully biopsied this embryo, removing 2 cells that can be tested and leaving an intact 6-cell embryo. Now you'll notice a second embryo in which there is more fragmentation that is obscuring your view of all of the 8 cells. We're going to make our hole in the outer shell, that is the zona pellucida, right over this area of fragmentation. The fragmentation is just cellular material that can never result in any baby. And that is why, if we have a choice, we try to make the hole right over that fragmented material so that there's no chance we'll damage any of the true blastomeres of this embryo. Once we make the hole, we can remove those fragments so as to get a better view of the embryo, but more importantly, we can actually remove, once again, 2 out of 8 cells so that we can test whether or not this embryo can genetically result in a viable baby without severe lethal disease. Now we're putting a much larger pipette through the hole that was created by the smaller drilling pipette, and we're going to decide which one of these blastomeres can be most likely gently teased out without damaging the rest of the cells of the embryo. We're in the process now of trying to gently pull this cell out through some of the fragmented areas and through the hole in the zona pellucida without damaging either this cell or any of its surrounding cells. That biopsy looked relatively easy because the cell was not very tightly attached to its other components in the embryo. You will see eventually, however, that some cells are very difficult to remove because what is called compaction has begun. Now, in these first two embryos, which we've just biopsied, compaction had not yet begun, so it was relatively easy to remove the two cells without damaging the rest of the embryo. In the third embryo you're about to see, compaction has begun, and there are tighter connections between the blastomeres of this embryo, and you'll see that it is relatively difficult to get the cell out without either damaging the cell itself or the surrounding cells of the embryo. Right now you're seeing that we're carefully making a hole in the outer shell by actually squirting in the usual fashion some acid tyrose solution on that zona pellucida, and once the hole has been made, then we get the embryo reoriented so that we can place a much larger pipette through the hole. This is the embryo biopsy pipette. Now, in this embryo biopsy, you're going to see it's somewhat more difficult to tease the cells out because this embryo is advanced several hours farther along than the previous two you saw, and therefore these 8 cells are no longer functioning so much like independent units, but have begun to stick together more and are actually functioning more as an entity, as an 8-cell entity that has 8 separate cells. It's at this moment of compaction that you can see well demonstrated here that not only is it more difficult to do the biopsy, but possibly there may be the beginning of differentiation of the individual cells of the embryo. The very last cell that you see that we're going to biopsy really will not tolerate the procedure and will be damaged by it. But luckily, the embryo itself has not been damaged. We still have one cell to examine, and we will not have really hurt the embryo in any way, despite the very great difficulty of doing this procedure at this stage. It has been demonstrated that removing 1 or 2 cells from an 8-cell embryo will not hurt the growth and development of that embryo. But if you remove more than 1 or damage more than 1 or 2 cells in an 8-cell embryo, that will severely limit its ability to develop. Detailed studies in experimental animals, not in humans, have clearly demonstrated that when you remove 1 blastomere from a 4-cell embryo, you will severely hurt that embryo. But removing 1 or 2 cells from an 8-cell embryo will not hurt its future development. Here you see the blastomeres from the first embryo lined up nicely and ready for genetic testing. This is from the second embryo, 2 beautiful intact cells, each of which is potentially able to develop into a baby, and the single blastomere from the third embryo.